Hey, Honors Chemistry, it's Wednesday, May 6th, and I want to thank you for working so hard on Thursday last week because I had a 19.5-minute film and you guys rose to the occasion and did really well on the quiz. I'm proud of you. Thank you. So now what we're going to do is a couple reactions at the beginning of class in my basement here. The first reaction is going to be aluminum foil. There we go, aluminum foil in copper 2 chloride. Copper 2 chloride is just a salt. There it is. It's kind of green in color, and you can see. Now you can also use copper 2 sulfate, and it's kind of a blue chunky thing, and it needs a catalyst like salt, table salt, in order to make this reaction work. But this one with copper 2 chloride does not need a salt. We'll go ahead and we'll mix a solution of copper 2 chloride, and we'll stick it in here, and we'll stick the aluminum foil in, and you can see I've already got it started for you, so you don't have to wait around. And you can see right here that I've harvested some copper from that solution. It's pulling the copper out of the copper chloride solution and deposited it on the side of this aluminum. It's a single displacement reaction. And so the aluminum is going into solution with the chlorine, and you're getting aluminum chloride, and it will turn, after a while, it'll turn into aluminum chloride, a clear solution. In fact, you can go ahead and see that this is elemental copper because we can shake it off the side of this aluminum foil. We probably ought to do that once in a while, you know, to make room for more aluminum to have contact with the chloride solution. Okay, and so that's copper on the bottom. We'll write that equation. It's a little warm. It's a little warm. I didn't heat it or anything. It's just the enthalpy of reaction. Okay, so we're going to go ahead and fire up this blowtorch here in my basement. Not a problem. Let me go ahead and turn that down. There we go. We got a blowtorch going. And you guys may have remembered this earlier in the year. I've got a mortar and pestle right here. We're going to take some tongs and some magnesium ribbon. We're going to fire that baby up. We're going to make some magnesium oxide. Right after you've looked at it for a second, you probably ought not look at it for any longer. All right, once it gets cool, you're going to see that it's a white ash. You can see that. And I'm going to go ahead and drop this white ash into the mortar. And I'm going to go ahead and crunch it up a little bit with my pestle. And I'm going to put a little bit of water in there. Does anybody remember when a metal oxide has a little water with it? Where's my, there it is. My distilled water, put a little water in there. There we go, that's good enough. We're going to take our little rubber policeman, you know, our glass stirring rod with spatula. We're going to stir it around a little bit. And then we're going to dip it with some Hydrogen paper to see if, in fact, we have a base. Because if it is magnesium oxide plus water is magnesium hydroxide, like we said it should be, then it should be making hydroxide ions right now. And so therefore, it would be basic. So let's just dip this in there and see if we get a little bit of a greenish, darkish color on this Hydrogen paper. If you look at it, hopefully you will see that, look at her on the tip, boop, it looks green. It is. The reason it looks green is because it is green. And so we can see that we've got us a base. There, it's a little bit better now. There, it's pretty obvious now. If you're, at least if you're with me. All right, it's green. So that means we've got a base because it's probably got a pH of about 8 or 9. Okay. All right, so let's go ahead and get those glasses off. Lab apron off. Let's talk about this. I'm on page 631. 631. Now, it says on the top, oxidation-reduction reactions involve the transfer of electrons. Oxidation involves loss of electrons, whereas reduction involves gain of electrons. So we call the oxidation an increase in oxidation state, and we call reduction a decrease in oxidation state. Well, what does that mean? Well, it means Leo the lion says grr. Leo the lion says grr. Loss of electrons is oxidation. Gain of electrons is reduction. So remember good old Leo, and you got this down. Now, if you lose electrons, you're losing negative stuff, so you get to be more positive. More positive. In other words, what do you call it? Oxidation state goes up. But if you gain electrons, electrons are negative stuff, so it's going to be more negative than it was before. And so you've gained negative stuff, became more negative, so the oxidation state went down. That's pretty much it for oxidation reduction, which we should call reduction oxidation since we call it redox. But that's fine. You can see the rules that we went over on page 631. Now let's go ahead and take your quiz that you did last Thursday. In my demo, I put zinc into hydrochloric acid. And I made zinc chloride, which was black, and released hydrogen gas. Now we can balance this out by saying we got one zinc. We need two here. All right, and the zinc is 0 because it's elemental form. Hydrogen is +1 because it always is, unless it isn't. Chlorine is -1. That's why we went crissy-crossy and got a 1,1 subscript. Over here, zinc is +2 because on the periodic table, zinc ends in 4s2, 3d10. So the 4s2 electrons go away, and we have a +2, and chlorine is still -1. And there's 2 of them because it balances that out, and that's 0 because it's an elemental form. So what we have for zinc is that zinc is going, I'm going to go with a different color. Zinc is going up. I know I did all this before, but this is a review. Zinc is going up in oxidation numbers, so it's zinc is being oxidized. We say that's oxidation. And hydrogen is being reduced because hydrogen is going from +1 down to 0. So that's called reduction. We say that hydrogen is reduced. We say that zinc is oxidized. We say that hydrogen is reduced but hydrogen is the oxidizing agent. Hydrogen is the oxidizing agent that is oxidizing zinc. What does it mean that hydrogen is oxidizing zinc? It means hydrogen is stealing electrons from zinc and making the oxidation state go up. Because when you steal negative stuff, then the oxidation state goes up. We say that zinc is being oxidized, and zinc is reducing. Zinc is reducing hydrogen. So it is the reducing agent that is giving electrons to hydrogen. So is zinc being oxidized? Yes. By whom? By hydrogen. Is zinc a reducing agent? To whom? Who is it reducing? It's reducing the hydrogen by giving it an electron. And electrons are negative. So it's reducing the hydrogen. Hydrogen is being reduced by whom? By the zinc, by the reducing agent. Zinc is being oxidized by whom? By hydrogen. Hydrogen's the oxidizing agent. So we got oxidation and reduction. We got reducing agent and oxidizing agent. So the one that's being reduced is an oxidizing agent. The one that is being oxidized is a reducing agent. I've been going for 13 minutes now. 2 demonstrations later. We got to get to those demonstrations. So again, it's going to be a long discussion. I'm sorry, but this is kind of hard at the outset. Leo the Lion says, Gur, it's all about transfer of electrons. Okay, so let's take this example right here. Looks like we got some more copper. Well, we're going to go ahead and we're going to take aluminum, comes into the dance with copper 2 chloride, and begins to dance with chlorine. And copper goes and dances by itself and falls to the bottom. Aluminum is 0 in elemental form. Aluminum becomes +3. Aluminum gets oxidized. Now, we got copper. I'm sorry. Yeah, we got copper here, and it is copper 2. But we got to go like this. +2, -1, +3, -1, 0. So the copper is being reduced. And that's an oxidation reduction. You can see that for every 1 oxidation, there's 1 reduction. And the chlorine is just a spectator. It just rides its way through. It's -1 and it's -1. Now we got half reactions. Half reactions go like this. Well, let's first of all balance the equation. We've got 1 aluminum, 1 aluminum. We got 3 chlorines, we got 2 chlorines. So we're going to go 3 and 2, and we're going to go 2. And copper, there would be 3 coppers. Let's see if that's right. 2 aluminums, 2 aluminums, 3 coppers, 3 coppers, 6 chlorines, 6 chlorines. Okay, so the oxidation half reaction looks like this. 2 aluminum at 0 becomes 2 aluminum atoms at +3. Okay? And chlorine's going along just for the ride. Now, how do you get it to go from 0 to +3? Well, it loses electrons. And so what have you got? If you want to balance atoms, you got the atoms balanced, all right? But if you want to balance charge, you got to subtract 3 from this to get 0 on both sides. So you're going to add 3 electrons. Now the copper, there's 3 coppers. This is the reduction part of it. There's 3 coppers that are becoming 3 copper. These are coppers +2. I'll call it 2+, that are becoming 3 coppers at 0. So it's being reduced. How did it get reduced? Well, it got reduced by adding some electrons. How many electrons? How about 3 electrons? Does that bring it down? Well, let's see. The total charge over here is +6. So how do you get it down to 0? -3 is not going to do it. You're going to need 6 electrons. You're going to need 6 electrons to get it down to 0. +6 minus 6 is 0. Well, then let's go up and fix this one. Obviously, that should be a 6. There's 2 aluminum atoms. And so the charge over here isn't +3, it's +6. And so how do you get +6 down to 0? You're going to need to add 6 electrons. So what do you have when you go with elemental aluminum? You got a charged aluminum and 6 electrons. What do you have over here when you have a charged copper? You got to add some electrons to bring it down to 0 elemental copper. These are the 2 half reactions. And there's a little bit more to it than that because we got to add back in the chlorines. And we'll learn about how to do that tomorrow. See you.